Okay, I stop sharing the screen and I stop recording. Okay, as I announced before the break, so this is now section 3.5. I skipped 3.4. And that's the last section about this more geometrical properties, about the geometrical properties of vectors and how we can use them to prove geometrical results. So the last section is now about a different product, and it's also kind of special. The dot product is easy to say what we mean by it in 2 components, 3 components, 4 components, 5 components. This one is now different. So this is, at least for our class, this is very specialized to 3 components. So you don't have a cross product for 2 vectors, for example. So this is now what's called the cross product. And as I said, sometimes you also find different names like skew product. And so here the idea is kind of different than the dot product. The dot product I told you in physics is if you pull, for example, a sled with a certain angle and the sled moves, the dot product allows you to calculate the work done on the sled because it gets faster if you pull. And the cross product is now more connected to rotation. And so I have a wrench here. Okay, so something like this, and everyone knows how this works. So think about this is a vector pointing from here to here in this direction. No? So this is the vector of my handle. And now everyone knows, so this is one vector. And everyone knows if I pull now in this direction, and let's say, okay, not in my case, but imagine it would be here inside in a nut. Then when I pull here, we see this one rotates. Yeah. So essentially, this is one vector. The pulling vector is the other vector. And what happens is we get a rotation. And a rotation, now how do we describe a rotation? Turns out rotation we can describe by the axis of the rotation. And you can say how much force is there. So the length of the vector gives you the force, the rotation force, which we usually it's called the torque. So it turns out one vector, another vector gives you this vector. And that's what the cross product does. And also now when you think about how do you, if you ever have changed the tire on your car, how do you pull? Usually you try to pull perpendicular because then you generate the largest torque. Nobody will usually pull in this direction because if you pull like this, for sure you generate torque, but you lose a lot of your force. And the worst would be, for example, pulling in this direction, then we know it doesn't move at all. Okay, so you try to be perpendicular. So this time, this vector is the biggest if we're here perpendicular. So it's not proportional to the cosine because the cosine would be 0 here. This time, okay, that is actually where physics have to do measurements. Turns out this time it's the sine. Okay, so this is the picture you should have keep in mind. One vector, another vector, and the result is a rotation with a vector which is perpendicular to the plane of these 2 vectors. And it's the biggest if we have a 90-degree angle here. Yeah, and the direction is given by what's called the right-hand rule. No? If I pull like this, then the vector would go down because we rotate in this direction. No? Okay, so it's the right-hand rule which tells us the vector, and the force is proportional to the sine of the angle between them. Okay, so much for the motivation. So, okay, so cross product you can say again in physics would be you have 2 vectors, u, that's the handle of my wrench. Then another vector v, that's how I pull. Keep in mind, usually the v would be here at the end. You'd pull at the end, no? Okay, and the result is a torque, a rotational movement around a vector, w, And so W means we rotate around W, and the length of W is essentially the force of rotation, which is not called force at this time, it's called the torque. So W is the vector that describes the rotation. It means it rotates around the axis of W, and if the vector goes longer, it's more torque. If the vector is shorter, it's less torque. And W can also point down if this vector would point in the other direction. Okay, so the vector W is perpendicular to U. W is perpendicular to V. This is one property. The other thing is W, the length of W, remember that's the torque, is proportional to U. If you have a longer handle, you have more power. If you pull harder, you have more power, but it depends also on the angle. So the angle should be 90 degrees, that's the best. If you have an angle like in my picture, less than 90 is less. So it turns out it's the sine of theta. And we have to take absolute value because it might also go down. And then finally, so two vectors define a plane. So there's a vector up and a vector down. And the direction of W is given by the right-hand rule. So from U to W means it goes up. If it's W on the other side, it means like this, it will go down, it rotates in the other direction. Given by right-hand rule. This is just how we translate pulling into a rotation. Okay, so now you can say, okay, these are nice things which we like to have. The question is, can you figure this out? Okay, in this class, I don't do the calculation, but it turns out really based on these three things, you can find a formula for W. And this formula is the formula for the cross product. Like I said in my Calculus 3 class, because it's the cross product also shows up in Calculus 3, which you have not maybe been to until now, but it's just a side note. So it turns out if you give me half an hour, I can actually show you based on this what the formula is. In this class, I'll skip it. So I just tell you the formula first. So it turns out if U has three components, U1, U2, U3, and V has three components, which I call V1, V2, V3. Then, based on these three properties, you can show that we get the following result. The cross product, the first component is U2 times V3 minus U3, V2. So 2 and 3 just changed position. Then we have U3, V1 minus, and again, 1 and 3 just changed position. And then, oops, sorry, I like to start with U all the time. Then we get U1, V2 minus U2, V1. So this formula you can derive, if you say this and this and this has to be true, you come out, there's only one possibility and that's it. That is solving this problem, no? Okay, and this is called the cross product of U and V. Okay, now you can say, how in the world can I remember this? And one way of doing this is that I just put a remark. It's like a little bit helping how to calculate a cross product if you know already the determinant, but we know the determinant. So remark, symbolically, we have U cross V is determinant of, now row number 2 is U, row number 3 is V. U1, U2, U3, V1, V2, V3. But what do we write in the first row? And that's actually why it's symbolically, because it doesn't really make sense. You just write the unit vectors, E1, E2, E3. And then you do expansion with respect to row 1. So you do E1 times the determinant of this. Minus, remember, plus, minus, plus, minus E2 times the determinant of U1, V1, U3, V3, plus E3 times the determinant of U1, V1, U2, V2, and then you calculate this. So this is E1. Also keep in mind, maybe instead of E1, I write down what it means. It's our first standard vector. So whatever comes here comes in the first component. So it's U2, V3 minus U3, V2 minus the second unit vector, 0, 1, 0, times, then we have U1, V3 minus U3, V1 plus third unit vector 0, 0, 1 times U1, V2 minus U2, V1. And also in reality, you don't have to write this down. You just look up here. No? So you see, okay, this one goes in the first component. This one goes in the second component, but has a minus. So it's actually minus U1, V3 plus U3, V1. And we see that's the same as here. And then the last one has this. Okay, so this is something how I would try to remember the cross product. You write in the first line, just as a memory, oh, these are the unit vectors. So if you calculate this determinant, goes component number 1. You calculate this determinant, goes to component number 2 with a minus. And you calculate this determinant, goes in component number 3 with a plus. So, for example, again, if you calculate 1, 2, 3, cross 4, 5, 6, then you calculate the determinant of E1, E2, E3. Then we have here 1, 2, 3, 4, 5, 6. And what you get is, okay, for component number 1, E1, it's the determinant of 2, 3, 5, 6. So it would be 2 times 6 is 12, minus 15, negative 3. For E2, the second component, it's 1 times 6. It's 6 minus 3 times 4 is 12, so it's minus 6. But remember the minus, maybe I should also write it here. So it would be plus 6. And E3 is 1 times 5 minus 2 times 4 is again a minus 3. So this is how we can calculate cross products. And the interpretation is, this is the direction of my wrench. This is the direction of how I pull. This vector is an axis in 3 dimensions, and it tells me the rotation axis. And the length of this vector tells me how strong the rotation is. Okay, so this is how we calculate cross products. So now, first, some properties of this cross product.
Professor, what does that say up back a ways before the definition? If you, it says right hand side, I think.
No, right hand rule.
Oh, right hand rule. Okay.
This is this thing, no?
Oh, okay.
So when you rotate from U to V, then your thumb tells you in which direction it points.
Okay.
Mm-hmm.
And Professor, for your final answer that you just got, is it -2 or -3?
Also -3, 6, -3. That's what I got.
Thank you.
Maybe you can just, for example, 2 times 6 minus 15, yeah. And this one is 5 minus 8. Yeah, it should also be -3. Mm-hmm. Also right hand rule, no? Also this. from U to V, and then this is the axis of your rotation. So if it would be U to V like this, it would rotate in the other direction. Okay, so based on this formula, the next two results are actually easy to see. And again, this is just a collection of results. The first is more how to combine cross products. The second is more the basic algebraic properties. Again, don't learn these. No? Also, they're just properties for your homework. Look at them if you can use them. So I tell you which one are the most important ones, and they come right away out of this here. So this is just a list of results.